Welcome to the deep dive. Today we're tackling a really fascinating question. How has women's involvement in European science actually changed over the past, say, 3 decades?
Yeah, it's a big one.
We've got this really rich set of data here. It spans 1990 right up to 2023. Gives us a wide view across 14 key STEM fields, science, technology, engineering, maths, and medicine.
Right.
And our goal really is to look beyond just the overall figures. We want to understand the interesting shifts, the differences between scientific areas, and, well, what things look like for different generations of researchers.
Exactly. And we'll even take a quick look at how Europe stacks up against the U.S., Canada, Australia, Japan.
Ah, good point.
And we're not just, counting numbers. We're trying to understand the story behind the change. This huge amount of structured data we have, think of it like a massive record of scientific work. Who did what? Lets us really dig into these trends. We want to give you, the listener, clear insights, highlighting where we've seen real progress and also where the challenges in gender representation still lie.
And those challenges and the progress, too. That's what makes it so interesting, I think.
Yeah.
I mean, did you know that in some scientific areas in Europe today, women are actually the majority of the new researchers coming in?
It's pretty striking when you see it laid out.
It really is. But then you look at other fields and progress has been, well, incredibly slow. It's this contrast, this divide that we're going to explore.
Precisely.
So let's maybe start with the big picture. What does the overall growth of women in European science look like between 1990 and 2023?
Okay. Well, the first thing that just jumps out is the sheer amount of growth. The number of women scientists in Europe, it's increased dramatically over this time.
Right.
But, and this is important, the world of STEM is really diverse. So the patterns of this increase, they vary quite a bit. Depends on the specific field. Depends on the generation of scientists you're looking at.
Okay, let's get a sense of that scale then. Can you give us some specific numbers just to illustrate this overall trend?
Absolutely. So if we look at the overall percentage, back in 1990, women made up about 22.44% of scientists in Europe.
Okay, just over a fifth.
Exactly. Fast forward to 2023, and that number had risen to 40.23%.
Wow, okay. That's a substantial jump. Nearly doubling the representation in, 30-odd years?
It is. It shows real movement.
That definitely sounds like real progress. But like you said, it's not consistent across the board.
No, definitely not.
So let's get into those disciplinary differences. Which fields have seen the most significant increase? And maybe which ones have been slower to change?
Yeah, this is where it gets really interesting looking into the details. We've sort of identified a few groups.
Okay.
First, you have fields that already had, let's say, a noticeable female presence back in 1990, and they've just continued to grow steadily.
Right.
These include bio, so think biochemistry, genetics, molecular biology.
Right.
Also IMU, that's immunology and microbiology, neuro for neuroscience, and pharmacology-related stuff. These fields started with around a third of researchers being women, roughly. And now, they're approaching 50% by 2023. Almost parity.
So a pretty consistent climb in those areas. What about the fields that experienced the fastest rate of increase? Were they the same ones?
Interestingly, no, not exactly. The fields that saw the most rapid growth in women's participation were actually MED, so medicine, AGRI, agricultural and biological sciences, and NNVR, environmental science.
Oh, okay.
And to give you an idea of the speed, right? The fastest 1 percentage point increase happened in ENVR. It took just about 1.1 years on average for that single point jump.
That's quick.
It is. MED wasn't far behind at 1.28 years, and AGRI at 1.35 years. So these fields really picked up pace in terms of gender balance.
That's a big difference from what I suspect we'll hear about the slower growing fields. What's the story there?
Exactly. You're right. On the other end, we have what we've kind of called the math-intensive cluster. That's math, obviously, mathematics, COMP for computer science, PHYS physics and astronomy, and ENG, engineering. These fields, well, they consistently had low female participation right from the start in 1990.
And slow growth since then.
And relatively slow growth throughout the entire period we looked at, yeah.
How much slower are we talking, really?
Well, these are the fields where it took the longest to see even a small 1 percentage point increase in women's representation.
Right.
We're looking at a range from about 2.91 years in ENG, which is the fastest of the slow group, I guess.
Relatively speaking.
Exactly. Up to a considerable 3.89 years in COMP, computer science, for that single percentage point change.
Wow. That really highlights the difference in pace, doesn't it? And what was the starting point like in these fields? Were they all low?
Very low comparatively. ENG engineering had the lowest starting point in 1990, only about 5.61% female participation.
Just over 5%.
Yeah. And even though that nearly tripled, which sounds good on its own,
Yeah.
it only reached 15.88% by 2023. So it's still the field with the lowest representation of women overall.
So progress, yes, but from a very low base and much slower than elsewhere.
Precisely. It definitely makes you wonder about some of the underlying reasons for this persistent gap in these particular fields, doesn't it?
It really does. Now, this use of big data, bibliometric data, to understand these trends is fascinating. But I'm curious about the mechanics, how it works. What are some of the main challenges researchers face when you're trying to study something like gender in science this way, on such a large scale?
That's a really critical point, because the insights we get, they depend directly on how the data is put together and analyzed.
Right.
Our study, like many others, uses this structured big data from sources like the Scopus database. And we definitely encountered, I'd say, 3 main methodological hurdles.
Okay, let's dig into those. What's the first one?
The first big challenge is figuring out the gender of the authors. You see, unlike maybe some national records, these big global databases, they don't typically have a field for gender.
Ah, okay, so you have to infer it.
Exactly. Researchers have to infer gender, usually from author names using special tools, gender detection tools. We use one called NAMSOR, which gives a probability score for its predictions.
Okay.
And to be reasonably confident, we only included authors where the tool gave a score of 85% or higher for the gender assignment.
That makes sense, aiming for accuracy. But it still sounds like there could be some, well, inaccuracies or limitations.
Oh, absolutely. There are several. For one, not all publications have full first names, especially older ones, or maybe papers with huge author lists. And you really need those first names for the tools to work well.
Right. Initials aren't much help.
Not really. Then you also have names that are used for both men and women, unisex names, which can obviously be tricky. And importantly, the current tools mostly work with a binary understanding of gender, male or female. So we can't really identify non-binary individuals in the data using these methods.
That's a really significant limitation to keep in mind, especially now.
It absolutely is. It's like trying to sort everyone into just 2 boxes when, reality is more complex.
Definitely. Okay, so that's gender determination. What's the second methodological challenge you mentioned?
The second one is determining someone's academic age. Now, ideally, we'd know the actual age of every scientist, but that information just isn't usually available in these large databases.
Right. Privacy and practicality, I imagine.
Exactly. So we use a proxy, a stand-in. We look at the year a scientist published their first paper that's included in the Scopus database. This gives us an idea of how long they've been active in research, their publishing lifespan, so to speak.
So it's not their biological age, but how long they've been publishing as far as the database knows. How accurate is that as a stand-in?
It's generally considered a pretty good approximation, particularly in STEM fields. It's estimated to be about 80–90% correlated with biological age in these areas.
Okay, that's quite high.
It is. But it can be less accurate in different academic systems, or maybe for researchers who started publishing globally later in their careers, or perhaps took breaks. It's a proxy, not a perfect measure.
Understood. And the third methodological hurdle?
The third key challenge is figuring out which academic discipline each scientist primarily belongs to. Because people can move around, right?
Yeah, interdisciplinary work is common.
Very. So we did this by looking at the references they cited in their publications. The discipline of each cited paper is based on how the journal it appeared in is classified in Scopus, using their codes.
Ah, clever. So you look at what they're reading and citing.
Essentially, yes.
Yeah.
By looking at all the references a scientist makes over time, we can sort of find their main field, the one they cite most often. That's assigned as their dominant discipline.
That makes sense for established researchers who've published a lot, but what about those who are just starting out, or someone who works across fields?
That's a great point. This method definitely works best for scientists with a longer publication history, simply because there's more data, more citations to draw from.
Right.
For researchers with only a few publications, the assigned discipline might not be as precise. And also, just for simplicity, in this kind of large-scale analysis, we used a one scientist, one discipline approach.
Okay.
Even though we absolutely know that some researchers work across multiple fields, it's a way to simplify a complex reality to make the analysis manageable.
These methodological points are really important context. Thanks for explaining them. It helps understand the data behind the trends.
Definitely.
So now, let's look at that generational analysis you mentioned earlier. What does the data from 2023 tell us when we compare women's participation across different age groups, or rather academic age groups, within the same field?
Right. This is where we see some of the most, I think, compelling evidence of change happening right now. When we take a snapshot of scientists active in 2023 and group them by how long they've been publishing their academic age, we see really significant differences in women's participation levels between those groups.
Can you give us an example of this overall generational difference across all fields combined?
Sure. So for all STEM disciplines combined in Europe, in 2023, if you look at the, say, 41, 45-year academic age group.
Okay, established research.
Yeah, mid-career. The percentage of women in that group was around 20%.
20%. Okay.
But then, when we look at the youngest group, those with 5 years or less of publishing experience recorded in Scopus.
The newcomers.
Exactly. The percentage of women jumps to nearly 50%, 49-point-something%, basically parity.
Wow. That's a huge difference, from 20% to almost 50%.
It really is. It suggests a really significant increase in women entering scientific careers much more recently compared to, say, 20 or 30 years ago.
That's striking. Are there specific fields where this generational change is most noticeable, where the young cohort looks very different?
Definitely. In 2023, women actually made up the majority of the youngest publishing scientists, that 0-5-year group, in 6 STEM fields.
6 fields with a female majority among the newest researchers. Which ones?
Those are MU, Pharm, Neuro, Med, Bio, and AGRI.
A lot of the life sciences and related areas we talked about earlier.
Exactly. And what's more, they were also the majority in the next bracket up, the 6-10-year experience group, in 5 of those: MU, Pharm, Neuro, Med, and Bio.
So it's not just the absolute newest cohort.
No, it suggests a strong trend toward gender balance and even a female majority among early career researchers across many of these life science and related areas.
That's really positive news for those fields. But what about those math-intensive fields we talked about earlier? Does this generational shift look the same there? I suspect not.
Unfortunately, no. It's a very different picture. In math, co-MP, PHYS, and ENG, the percentage of women in those younger age groups is still hovering around 20%.
So even among the newcomers, it's still only 1 in 5.
Roughly, yes. And what's more, if you look at the older age groups in these same fields, they often have even lower representation, sometimes down in the 11-13% range, and even below 10% in the older cohorts in engineering.
So while there is some generational shift upwards, it's much, much less dramatic in these areas.
Much less dramatic.
Yeah.
It seems whatever factors are influencing participation in these specific fields might be, well, more entrenched or slower to change.
The imbalance persists even among younger researchers in those fields, albeit maybe slightly less severe than for older generations.
That's a good way to put it.
Can you give us a specific example, maybe illustrate this generational change within one of those disciplines, like engineering?
Sure, let's take engineering, ENG. In Europe in 2023, among the young researchers, let's say the 6-10 years of publishing experience group,
Okay.
the ratio of men to women was about 5-to-1. So 5 men for every woman.
Still quite skewed, but okay, 5-to-1.
Right. Now, if we look at a more senior group in engineering, say the 36-40-year academic age group, that ratio widens significantly. It's about 12-to-1.
12 men for every woman.
Yes. And then if you go to the oldest group we measured, those with 46 or more years of publishing experience, the ratio is almost 20-to-1.
20-to-1. Okay, so that really paints a picture. While 5-to-1 is still far from balanced, it's a massive change from 12-to-1 or 20-to-1 in the older cohorts.
Exactly. It shows a clear, undeniable increase in women entering engineering in more recent years, even though they still make up a much smaller proportion compared to men overall in the field. It's definitely a sign of progress, albeit, as we said, a slower one than in other areas.
That gradual change in engineering is encouraging, I suppose, even if the numbers still have such a long way to go.
Yes, it points towards a direction, at least.
Now, let's maybe zoom out a bit again. How does Europe's progress or lack thereof in some fields compare internationally? You mentioned looking at the U.S., Canada, Australia, Japan.
Right. So our analysis indicates that Europe's overall trend, that general increase in women's participation we saw, it's actually pretty comparable to what's been happening in the USA. Similar trajectory overall.
Okay.
However, the growth in Europe seems to have been slower than in Canada and significantly slower than in Australia. Australia seems to be moving faster towards gender balance in science based on this data.
Interesting. And Japan.
Japan really stands out. It has traditionally had a very low level of women's participation in science compared to these other developed nations. And the data shows extremely slow rates of increase, particularly in those math-intensive disciplines we discussed, and also notably in chemistry.
So Japan is lagging quite far behind these other regions.
It appears so, yes, based on this bibliometric data.
It's interesting that some countries are seeing faster changes than Europe. Are there any similarities, though, in which fields are driving the growth internationally?
Yes, that's actually quite remarkable. Remember those 3 fields we highlighted for rapid growth in Europe?
ME, AGRI, and NVIR. Medicine, agriculture, environment.
Exactly. It turns out those same 3 fields, AGRI, NVR, and MA, are key drivers of growth in women's participation, not just in Europe, but also in the USA, Canada, and Australia.
Really? The same 3 everywhere?
Pretty much, yeah. It's quite consistent across these regions. It really suggests there might be some shared, perhaps global, factors influencing women's entry and progress in these particular scientific areas.
That is fascinating. Now, thinking about the impact of all this evolving gender mix must have some pretty significant consequences for the scientific community itself, right? For how science gets done.
Oh, absolutely. It has to. One important consequence, we think, is the potential for decreasing isolation of women scientists, particularly in those math-intensive fields where they've historically been such a small minority.
Right. Going from being maybe the only woman in the room to one of several must make a difference.
Exactly. When we compare the experience of older generations where women might have been, 1 in 10 or 1 in 20, to younger generations where the ratio is closer to, say, 1 in 5, the day-to-day experience of being a woman in these fields is likely to be quite different. And that could lead to, well, more diverse perspectives being heard, maybe different kinds of collaborations, a shift in the dynamics.
That makes a lot of sense. Less isolation could certainly foster more supportive environments and potentially improve retention, too, you'd think.
That's definitely a hope, yes.
What other practical effects might we see or anticipate from this shifting gender balance, especially as those younger, more balanced cohorts move up?
Well, as the gender balance changes more broadly, we can definitely anticipate practical effects on work environments and institutional cultures. I mean, institutions will likely need to adapt further to a more diverse workforce.
How so?
This could involve ongoing changes in policies, maybe different kinds of mentorship programs, perhaps unconscious bias training becoming more critical, and just generally evolving the overall workplace culture to ensure these environments are genuinely fair and inclusive and supportive for everyone, regardless of gender. It's an ongoing process.
It sounds like a necessary adaptation as the demographics change.
It really is.
This has been a really, really insightful deep dive into this data. It paints a complex picture. To try and bring it all together, what are the main takeaways you'd want our listeners to remember from all this?
Okay. I think the key picture is one of definite progress, but progress that is happening unevenly. That's the main thing.
Uneven progress.
Yes. We've seen substantial growth in women's participation in European science overall, which is great, and particularly strong growth in many life science and environment-related fields, where younger cohorts are near or at parity.
Right.
However, those more mathematically focused disciplines, math, physics, engineering, computer science, they continue to lag behind quite significantly. The growth is slower, the starting point was lower, and the gap persists even in younger generations, though it is narrowing. So the data on different age groups, it does give us a hopeful glimpse, perhaps, of future trends in many areas. But achieving true gender balance across all scientific fields, that clearly remains a real challenge.
A challenge indeed. And that brings us perfectly to our final thought for you, the listener. Considering these trends, the progress in some areas, the persistent lag in others, what specific steps, what interventions, maybe in education or within research institutions or at the policy level, might be most effective in accelerating the inclusion of women, particularly in those scientific fields where progress remains marginal?
That's the crucial question, isn't it?
It really is. And perhaps just as importantly, how can we ensure that the increasing numbers of women who are entering science are not only welcomed, but are also supported, retained, and encouraged throughout their entire careers? This data, as we've seen today, provides a really vital foundation for starting or maybe continuing these important discussions.
Couldn't agree more.
Thanks for joining us on this deep dive.